Hi everyone. In today's video, we're going to continue our discussion on substitution and elimination reactions. This time, we're going to talk about how to predict the product of a reaction and figure out when we're actually going to go through a substitution reaction or an elimination reaction. The key thing to note here is that often in organic chemistry, whenever you place a substrate in the presence of a reagent, there are often more than one product formed. And so a key skill in organic chemistry is being able to predict all plausible products in a particular organic reaction and then identifying the major products in that reaction. So to harness this skill, there are actually three steps that are required whenever you look at an organic reaction. The first step is to determine the function of the reagent, and then you want to analyze the substrate and use both of those information to determine the expected mechanism or mechanisms that are plausible in the reaction. And then once you do that, then you need to consider any relevant regiochemical and stereochemical requirements and outcomes of the reaction. So we're going to take these three steps step by step and see how we can essentially do all three of these. Okay, so our step one is determining the function of the reagent. So remember now that we've learned two different forms of reactions now. We've learned about substitutions and eliminations. Substitutions require strong nucleophiles, right? So you need a nucleophile that can attack your alkyl halide, and eliminations require strong bases. So you need a base that can deprotonate the beta hydrogens in your alkyl halides. And also recall that nucleophilicity and basicity are actually two different things. So these are not necessarily the same thing. The first of which is that nucleophilicity is a kinetic quantity and basicity is a thermodynamic quantity. So one is about rates and one is about equilibrium. And also, nucleophilicity is a measure of how electron dense and how accessible the electrons are towards nucleophilic attack. Meanwhile, basicity is a measure of how stabilized that electron density is in a molecule. So once again, when it's talking about a kinetic quantity, you're talking about a pathway with nucleophilicity, and the other is talking about stability and a thermodynamic quantity. Okay, so to illustrate how nucleophilicity and basicity do not necessarily track with each other, let's consider a molecule bromide. I think we will all agree that bromide is electron dense, and those electrons in the bromide are freely accessible. Therefore, bromide we can consider a strong nucleophile. However, we can also all agree that the electrons in bromide are fairly stabilized due to the size of the bromide atom. And this actually makes bromide a fairly weak base. And recall that the pK of HBr, which is the conjugate acid of your bromide, is -9. So this is an experimental quantity that is also supporting our idea that bromide is a really weak base. So notice that bromide, being a good and strong nucleophile, is also a weak base. So once again, these two things do not track with each other. Okay, so now what we're going to do is classify common sets of bases and nucleophiles by how strong they are as bases and how strong they are as nucleophiles. So what you can see here is a table with four columns. The first column is strong base, weak nucleophiles, strong base, strong nucleophiles, weak base, strong nucleophiles, and then weak base, weak nucleophiles. So here are our variety of bases and nucleophiles that we typically use in organic chemistry. So under the column of strong base weak nucleophiles, a common theme that I'm hoping you're seeing is that these are bulky molecules. So you're looking at your tert-butoxide, which is pretty bulky, which makes those electrons pretty inaccessible for nucleophilic attack. And so it remains as a really strong base, but a weak nucleophile. The same can go for your DPU and your DPN. These are bulky bases that end up being strong bases but terrible nucleophiles here. On the flip side, you also have your hydride ion, which is incredibly small, and those electrons are pretty tightly packed to that hydrogen atom, making those electrons pretty inaccessible for a nucleophilic attack. However, it is an incredibly strong base if you think about the pKa of H2 being about 35. On your strong base, strong nucleophile column, what you typically will see are your alkoxides and your hydroxide anions. On the alkoxide end, you're looking at R groups that are relatively small, so like methyl and ethyl, and that's the reason why these would still be strong nucleophiles because those extra electron density are pretty accessible for nucleophilic attack. And then you have your column of weak base, strong nucleophiles. So these are compounds in which their electron density is fairly stabilized. So you have your big halides like your iodide, bromide, and chloride. Although these are accessible electrons, they are also fairly stabilized due to the electronegativity and the size of these halides. You also have your sulfur-based nucleophiles, so your thiolates, your sulfides, your thiols, and what have you. These are all going to be considered strong nucleophiles because they have freely accessible electron density, but they're pretty weak bases if you actually consider how stable these electrons are on a large sulfur atom. Okay, and then on your column of weak base, weak nucleophiles, this is where you typically just have your neutral oxygen compounds like water, methanol, ethanol, and what have you. So your alcohols are typically considered weak bases and weak nucleophiles. Okay, so it's important that you're actually able to really get a good grasp of the nature of your reagents and figuring out if they're strong or weak bases or nucleophiles. But once you do that, then we can start to determine the expected mechanism of your reactions. So in order to determine the expected mechanism, the first thing we have to do is analyze the substrate that we're dealing with. And right now, we've only learned about alkyl halides as substrates, but there are three categories of alkyl halides that we've learned about. We've learned about the primary, the secondary, and the tertiary alkyl halides. So if you're able to determine that, that actually gives you a good idea of how these substrates are going to behave. So let's start by analyzing the primary alkyl halide. Okay, and then the way we're going to structure this analysis is by we're going to first describe each of those alkyl halide classifications in terms of just like how we would think about these substrates. And then we're going to look at how these substrate will react when it's in the presence of the four different categories of reagents that we described in the previous scene. So starting with the primary alkyl halide. So the first thing about primary alkyl halides that we have to always know is that that alpha carbon on the primary alkyl halide is highly accessible for nucleophilic attack. However, a primary carbocation is too unstable to form. So this has some implications. So the first implication is that the SN2 process will occur as long as you use a strong enough nucleophile. And the E2 process will also occur as long as you use a strong base. And then if you use a reagent that is classified as a strong nucleophile and a strong base, then both your SN2 and your E2 will occur. However, the products gotten from the SN2 process will be the major product because ultimately that alpha carbon is incredibly accessible for a nucleophilic attack. So your SN2 product will still be major. Okay, so now let's do some examples. The first one is taking a primary alkyl halide with a weak base, strong nucleophile. All right, so here's example number one. So primary alkyl halide with a weak base, strong nucleophile. So you're dealing with a strong nucleophile and a weak base, which means your SN2 process will be your primary product process. So you're looking at an SN2 only process here because your base is too weak. So now let's look at the reaction with a strong base weak nucleophile. Okay, so here's your example of your strong base weak nucleophile. And so you react that with your primary alkyl halide. So your E2 product, which is your alkene, will be the only product formed here. So now let's look at the primary alkyl halide with a strong base, strong nucleophile. In this case, now this is where you have that competition between your substitution and your elimination because both of those are going to be possible with a strong base, strong nucleophile. So you're going to get a substitution product and an elimination product. However, because of how accessible that primary alkyl halide is, your SN2 product is the major product, while your E2 product is the minor product. Lastly, reacting your alkyl halide, your primary alkyl halide with a weak base and a weak nucleophile, this is just weak sauce. So nothing can happen because you can't form a primary carbocation, it's too unstable to form, and you have a too weak of a base or a weak of a nucleophile, so your SN2 or E2 process cannot occur. So there's going to be no reaction in this particular case. Okay, so that's it for primary alkyl halide. Now we're actually going to go to a tertiary alkyl halide. So we're going to the other extreme end, and then we'll end with the secondary alkyl halide. Okay, so now for the tertiary alkyl halide, the alpha carbon in this case is highly inaccessible. So this alpha carbon is not going to readily undergo nucleophilic attack at all. However, your tertiary carbocation is indeed stable enough to form, which opens the door to SN1 E1 processes. So the implications of these two things is that your SN2 process will never occur with tertiary alkyl halides, regardless of how strong the nucleophile is, because you're dealing with a highly inaccessible alpha carbon for a nucleophilic attack. However, your E2 process will indeed occur as long as you use a strong base, because the moment you start having these tertiary alkyl halides, now you have many options for beta hydrogens that could be deprotonated. So your E2 process will certainly occur in the presence of a strong base. However, given that you can indeed form tertiary carbocations, as long as you don't use a strong base in the solution, then the reaction is just going to wait there until a carbocation forms, and then you can go through a substitution or elimination process. Okay, so this time we're going to try to react a tertiary alkyl halide with a weak base, strong nucleophile. So let's think about this, right? So we can't go through an SN2 process because the tertiary alkyl halide alpha carbon is highly inaccessible. You cannot go through an E2 process because you're dealing with a weak base. However, if you allow this tertiary alkyl halide to form a carbocation or go through a loss of a leaving group, then that sulfur can then attack your carbocation in an SN1 process, which would then result in your substitution product. Okay, so once again, that's pretty much all you're going to get really when you're dealing with a strong nucleophile weak base and a tertiary alkyl halide. But now, if we take the same alkyl halide, but now reacting your tertiary alkyl halide with a hydride ion, now you're dealing with a strong base and a weak nucleophile. It's not going to wait for a carbocation to form. It's going to very easily deprotonate one of the beta hydrogen positions to form your alkene. And so you're going to get your E2 product only in this particular reaction. React your tertiary alkyl halide now with a strong base and a strong nucleophile like your hydroxide. Remember that you can't ever do an SN2 because of that really inaccessible alpha carbon, or you have a strong base, so it's not going to wait for the carbocation to form. It's going to go through an E2 process once again to form your alkene. And then lastly, take your tertiary alkyl halide and react that with a weak base, weak nucleophile. So now you have a reagent that is incredibly weak sauce. So it's going to just wait there until a carbocation is formed. A carbocation can indeed form in this particular reaction, but once you do, you're going to engage in both an SN1 and an E1 reaction to form your SN1 and E1 product. Okay, so both your substitution and your elimination product to form in this particular reaction. So now let's finish up with our secondary alkyl halide. So with your secondary alkyl halide, you're kind of dealing with a mixed bag here. So your alpha carbon is somewhat accessible, but also somewhat inaccessible. So you really kind of are in this middle ground of accessibility. And then when your leaving group is your halide, your secondary carbocation is typically not also very stable enough to form. So your SN2 process will actually still occur as long as you use a strong nucleophile. And then likewise, your E2 process will also occur as long as you use a strong base. And then both your SN2 and E2 processes will occur as long as you use something that is a strong nucleophile and a strong base. However, experimentally, we've seen and observed in almost all the cases that our E2 product is the major product. And this can be somewhat explained in the sense that the alpha carbon is still somewhat inaccessible. And so the easier route to go is for your base to deprotonate the beta hydrogen over your nucleophile attacking the alpha carbon. Okay, so let's look at some examples of this. So take your secondary alkyl halide and treat it with a weak base strong nucleophile. And this kind of makes sense. You will get your SN2 product only. Treat your secondary alkyl halide with a strong base, weak nucleophile. This time you get your E2 product exclusively. Treat your secondary alkyl halide now, this time with a strong base and a strong nucleophile. This time you get both your E2 product, but also your SN2 product as well. However, your E2 product is going to be the major product in this particular case. And then treat your secondary alkyl halide with a weak base, weak nucleophile. And you would typically get no reaction in these particular cases because once again, the secondary carbocation is typically not very stable enough to form with your secondary alkyl halide. Okay, so all of that stuff we just did can actually be summarized in the table I'm showing you right here. This table is in your textbook. It's incredibly important that you know this table, but it's also even more important that you're able to understand why this table is categorized in this way. So once again, just sort of take your time to think about this table and think about how this is reflected in those reactions that we just did in the previous scenes. Okay, so once you've figured out the mechanisms of the reaction and then you've also been able to get the product, it's also important to remember that these reactions can have regiochemical and stereochemical outcomes. So this we've already talked about in great details in previous videos and in previous classes, but I'm going to summarize the four reaction mechanisms and their regiochemical and stereochemical outcomes here. Okay, so let's think about the regiochemical and stereochemical outcomes of your SN2, E2, SN1, and E1. So for SN2, the nucleophile attacks at the backside of your alpha carbon, and then the stereochemical outcome is an inversion of configuration. For E2 reactions, the Zaitsev product is typically favored, so that's the more substituted product. But the Hoffman product, which is the less substituted alkene product, is favored when a sterically hindered base is used. The reaction is stereoselective, which is saying that the trans alkene is favored over the cis alkene. And the reaction is stereospecific, and that comes from that anti-periplanar geometry in the transition state, which dictates the stereochemical outcome of your alkene. For an SN1 reaction, the nucleophile attacks the carbocation, and rearrangements may occur when you have your carbocation, which would ultimately affect the regiochemical outcome of your product. And the stereochemical outcomes, just over half of your product would be your inverted configuration, and just below half of it will be the retained configuration. So we may say that the product mixture is almost racemic. For the E1 product, the Zaitsev product is always favored, so every single time favored. And just like for your E2, the E1 process is stereoselective, so that the trans product is favored over the cis product. Okay, so this is really it for trying to predict the product of a reaction, right? So once again, you have to figure out the reagent and the function of the reagent, then analyze your substrate and determine the mechanism of the reaction, and then lastly, consider your regiochemical and stereochemical outcomes to get your product. Thank you so much for watching this video, and I will see you in class.